Hey everyone! Welcome back to our channel. Today, we're diving into the exciting world of solar-powered electronics. But as many of you know, harnessing the sun's power isn't without its challenges. Think about issues like charging batteries efficiently and maintaining a stable voltage output. Intrigued? Let's dive in! Alright, let's introduce our project, the DIY Buck Boost Module. This nifty little device lets you charge a single-cell LiPo battery using solar energy or a USB-C port. Plus, it provides a stable 3.3 volts output, which you can easily adjust by swapping out just one resistor. Pretty cool, right? Let's dive into the details. First up, we need to choose our integrated circuits. For battery management, we're going with the CN3063, tailor-made for single-cell LiPo batteries. Its features include optimal single-cell charging with a preset 4.2 volts charge voltage, integrated power transistors, and thermal regulation for protection. This little chip ensures your battery charges efficiently and safely. Moving on to our next critical component, the TPS 63020. This IC is a powerhouse, offering high efficiency over a wide load range. It's designed for 1.8 volts to 5.5 volts input voltage, making it perfect for our LiPo range. Plus, it has a low quiescent current and an adjustable output voltage, which is just what we need for this project. It's like finding a unicorn in the IC world. Let's now delve into the schematic development. First, we're embracing the future with a USB-C port. It's not just about versatility, it's about embracing the tech that simplifies our lives. After integrating the USB-C port, we turn our attention to implementing the CN3063. This little chip is crucial for managing our LiPo battery. It's specially designed for single-cell batteries, ensuring efficient charging and safety. By using the CN3063, we're not just building a circuit, we're crafting a reliable power manager for our solar-powered project. Adding to that, we've integrated a P-channel MOSFET and a Schottky diode, allowing us to utilize two distinct power sources, the solar panel and the USB port. This setup prevents any interference between the two power sources, enabling our device to switch seamlessly between solar and USB power. It's like having a backup plan that's both smart and efficient. And for the charging power, we've decided on 3.6K resistors to cap it at a safe 500 milliamperes, ensuring both efficiency and longevity of the battery. Now let's shift our focus to the TPS 63020, a key player in our project. We've taken the manufacturer's suggested design as our starting point. We've configured it with a 1 mega ohm and a 180K resistor to nail that perfect 3.3 V output. And for those who love to tinker, remember, adjusting R4 can give you different voltages. Just check the datasheet for the formula. Here's where it gets even more exciting. We've added two 0 ohm resistors into the mix. Depending on which one you solder, the TPS IC can either enter a low power mode or operate normally. This choice gives you the power to optimize for energy efficiency. But there's a catch. In low power mode, if there's no load, the chip might enter standby, dropping the output voltage. It's a trade-off, but one that adds a layer of adaptability to our project. Okay, it's time to roll up our sleeves for some PCB design using KiCad. To make our lives a bit easier, we've chosen 0805 size components. They're just the right size for hassle-free soldering. Now, diving into the design, we group our components based on the blocks we defined in the schematic. It's like organizing a tiny electronic neighborhood where each part has its perfect spot. Once we've got our layout sorted, it's time to define the PCB dimensions and jump into routing. And let me tell you, routing traces on a PCB can be oddly satisfying. It's like electronic ASMR, just me, the traces, and a peaceful sense of order. But don't get too lost in the zen of it. Remember, the traces carrying more current need to be a bit beefier than the rest. It's all about balancing aesthetics with practicality. Finally, we add the ground plane, giving our PCB the stability and integrity it needs. And voila, our design is ready. It's amazing how a bunch of lines and components come together to form something so functional and cool. Now that our PCB design is locked in, the next step is to get it fabricated. It's always a bit thrilling to send off a design and wait for the physical version to come back. Fast forward a bit and here we are. The PCBs and components have arrived. And guess what? I ordered them with a stencil, making it way easier to apply the solder paste. It's like having a cheat code for soldering. Alright, let's get down to business. We apply the solder paste with precision. It's a bit like icing a very technical cake. Next up, the component placement. I've laid them all out, almost like ingredients for a cooking show. Today on Cooking with Circuits. Once everything's in place, it's time for some heat. We carefully apply hot air, watching as each component finds its home on the board. It's a bit mesmerizing, really, like watching a dance of technology and heat. It's the moment of truth, folks. Time to test our solar-powered creation. First up, let's see if we can harness the power of the sun. We connect the solar panel and watch the energy flow up to the battery connector. It's like catching a bit of sunshine in our circuit. Will it light up our electronic world? Let's find out. Next, we switch to our trusty USB power. Plugging it in, we're looking to see if our board recognizes and utilizes this more earthly power source. It's like giving our project a choice. Solar spa or USB power nap? Let's see which one it prefers. And for the grand finale, the battery test. We connect our LiPo battery, which is fully charged at 4.2 volts. Will our circuit deliver a steady 3.3 volts output? This is the moment of truth for our resistors, transistors, and ICs. Let's see how well they perform. That's all for our project journey today. If you're keen on diving deeper into the details, I've got good news. All the schematics, code, and design files are available on our GitHub. Just check the link in the description below. Well, we've got plenty more projects and experiments lined up, each one as exciting as this one, if not more. Make sure you're subscribed and your notifications are on. You won't want to miss out on the fun. Thanks for joining me on this electrifying journey, and remember, every step in this process is an adventure in itself. Keep experimenting, and until next time, happy tinkering!